Hi guys! In today's video we're going to be using a marshmallow gun to basically shoot Ed. So how this works is we load up the marshmallow, we use the pump to build up air pressure, and when we press the trigger it releases the marshmallow because of the release of air pressure. Now Ed's going to explain the actual physics behind it. Over to you, Ed. I give up!
No. So how the gun works, I put the marshmallow in the barrel of the gun and close it. And then I pump it up. This builds up the air pressure behind the marshmallow. By shooting the trigger, I release the air pressure behind it, which accelerates the marshmallow and shoots it. As so.
There you go, it works.
To calculate the pressure behind the marshmallow, we have to do a quick experiment to get some measurements. We're going to be shooting a marshmallow from approximately 9 meters at a roll, and we're going to measure how far the marshmallow drops in this distance.
Down a bit, down a bit.
Yeah, that's good. A little bit now?
Good.
Jacob, the video is...
Sasha will be proud.
I know.
I'm a good.
That had to curve on it. So as you can see from our previous failed attempts, the practical did not work. This is because if we shoot the marshmallow up here horizontally or downwards, it doesn't come out. We could shoot it upwards and measure the height, but we don't have the means of measuring that. Thanks for watching, remember to stay sciencey. As you can see in the previous clips, the experiment did not work. However, we're still going to go over the maths that we would have done if it had worked. To do this, to calculate the pressure in the marshmallow gun, we're first going to have to find out the speed it was launched, and to find out that we need the time it takes for the marshmallow to travel the distance that we were given. To do this, we're going to use the Resultant equations. These equations allow us to calculate the missing variables using 3 of them: from displacement, initial velocity, final velocity, acceleration, and time. We're given the displacement with h. This is how far the marshmallow dropped. We're using this to find out time because time throughout the entire process is constant. It also accelerated to gravity due to acceleration due to gravity, so a g. And we're trying to find out time. The initial velocity is 0 as we're shooting it horizontally, which means it has no vertical velocity. The Resultant equation we'll be using is s equals ut plus half at squared. If we sub in our given variables, we get h equals, sorry, that's going to be 0t plus half gt squared. We can cancel this out because 0 times anything is 0. So now we get h equals half gt squared. And rearranging for t, we get t equals the square root of 2h over g. Next calculation, we're using this value of time to calculate the initial velocity of the marshmallows that leaves the gun. So our given variable this time is the distance the marshmallows travelled, which in our experiment was 8.7 meters. The initial velocity, which will be the same as the final velocity. This is because there's no horizontal acceleration affecting it, and constant acceleration, or with 0 acceleration we have constant velocity. And then t will be our previous expression of 2h over g. We're going to be using the same equation again, s equals ut plus half 2at squared. So if we put in our known variables, we get L equals U, so that would be V square root of this plus 1 over 2 times 0 times t squared. We can get rid of this because, once again, it's multiplied by 0. Now we have L equals V square root of 2h over g. And if you rearrange for V, we get V equals L over the square root of 2h over g. This would be the initial velocity that the marshmallow has left the gun at. Our next calculation will be to find the acceleration of the marshmallow in the gun. So we've taken the length of the barrel of the gun, which you're going to denote with a small l. The initial velocity will be 0, and the final velocity will be our expression from earlier, which is this. And the acceleration is what we want to find out. And t doesn't really matter since we don't need this in the equation. Here we're going to be using a different suit of that equation. We're going to be using v squared equals u squared plus 2as. Subbing in our known variables, we get L over the square root of 2h over g squared equals 0 squared plus 2al. We can get rid of the 0 since it doesn't change anything. And then we can rearrange this equation for a. By doing this, we get a equals L squared g over 4hl, which is the length the marshmallow has travelled squared times the acceleration due to gravity over 4 times the height the marshmallow has dropped times the length of the barrel. This is the acceleration within the gun. Next, we're going to use this to calculate the force needed to accelerate the marshmallow at this distance. So we're going to be using F equals ma. So the mass of the marshmallow we would have measured with a weighing scale. And then the acceleration we got in the previous expression. So you have F equals L squared g m over 4hl. This is the force required to accelerate the marshmallow at a calculated velocity. Finally, we can use this to calculate pressure. Since pressure equals force over area, we can calculate area with the diameter. Area would be pi d squared over 4, which is the same as pi r squared, simply using diameter instead of radius. And since we have force from our previous expression, we have pressure equals L squared Gm over 4hl, which is force over the area, which would be pi d squared over 4. If we simplify this, we get L squared Gm over hl pi d squared. This means given these variables we can find pressure, which is the length the marshmallow has travelled squared times the acceleration due to gravity times the mass of the marshmallow over the height that has dropped times the length of the barrel times pi times the diameter of the marshmallow squared.
Wait. Ed, raise it slightly up. It went up.
You don't need any more. Come like me,